All right, you guys, let's take a look at this topic. In mathematics, a mean. A lot of you have heard of a mean before. The mean, if I wanted to find the mean of 2 and 8, a lot of you think a mean is where we would take these two numbers and we would add them up and divide by 2. 2 plus 8 is 10 divided by 2, the mean of this problem being 5. Well, that's actually referred to, what you're trying to do is called the arithmetic mean. The arithmetic mean, or sometimes called the average, it's where you add all the numbers up and divide by how many numbers you just added up. This is the answer to the arithmetic mean. What we're looking at today is called a geometric mean. All right, so arithmetic often has to do with addition. Geometric, we're talking about multiplication. Well, the way to look at a geometric mean is actually a very special proportion. Good news is we're great at proportions. If I wanted to find the geometric mean of A and B, all right, the answer to the geometric mean, which I'm going to call X, would go here and here. This is a setup of a geometric mean. So let's say we wanted to do the geometric mean of 2 and 8, just like we did before. All right, but before we did the arithmetic mean, which is a different process. All right, the geometric mean, we want to do what we just did here. We would put one of the numbers in that spot and the other number in this spot. It doesn't matter which one goes where, because remember, we're going to cross multiply. 2 times 8 is the same as 8 times 2. The geometric mean goes here and here. So if I want to find the geometric mean, I would cross multiply. 2 times 8 would give me 16, and x times x would be x squared. If I want to find the geometric mean, I'm going to square root both sides. All right? Technically, the answer would be either a positive or a -4, but here in geometry, we're generally looking at lengths. So we're normally going to look at the positive value, because remember, we're looking at what we can square to get 16. 4 times 4 sure is 16, but so is -4 times -4. This is how we find a geometric mean. Well, that's not so bad. We can generally handle that, all right? Where this becomes difficult is an application of that idea called the geometric mean theorem. The geometric mean theorem says if we take a right triangle and we draw the altitude towards the hypotenuse, I just drew the altitude towards the hypotenuse. Well, I had one triangle. Technically now I have 3. I got the small one on the left. I got the little bit bigger one on the right. And then I have the original one, which was bigger than those 2. The geometric mean theorem is the idea that so I'm going to put this, I'm going to come up with a couple of numbers, 9 and 16. The geometric mean theorem says there's actually 3 of those geometric mean proportions hiding in there. Remember, the main characteristic of a geometric mean proportion is that these two values match, okay? So in order to prove this real quick, I say quick, but it's going to take a little bit of time. I'm going to take the 3 triangles, and I'm going to break it up. I'm going to take this triangle over here, but I'm going to spin it a little so that it's in this position. So now C is up there, A is over here, and let's give this the letter D. The medium-sized triangle, I can just simply slide it over here, and it'll be in the same position that I just put the little triangle. A is up here, D is here, and B is here. Now the big triangle, this is going to be interesting. I have to flip that triangle here and slide it over here, I want them all three in the same position. So that big triangle, if I flipped it upside down, A is down here, C is up here, and B is over here. So I'm going to prove really quick that all of these triangles are similar. Well, first off, they all have a 90-degree angle. Well, if we look at the small triangle here, does everybody see this angle C here, which is right here? Well, that angle has to be the same as the angle C in the big triangle. Angle C, that's not a C. Angle C has to be congruent to angle C. That's the reflexive property. So I know that the little triangle and the big triangle are similar by this shortcut that we used during the last unit. The medium-sized triangle, angle B over here, is shared by the big triangle. So these two triangles are similar by angle. So I know they're all similar. If we have similarity, this means we can write proportions. Well, let's quickly copy over the values. So the little triangle, this CD was 9, CA is X, and AD is Z. The medium-sized triangle, we got Z, 16, and Y. Now here's the tough one, the big triangle. AC is X. Y, which is AB, goes down here. And CB. CB, this whole length, I got to add up 9 and 16, which is 25. So I have three similar triangles. Now I just have to make proportions. Now, the key with making a proportion, let's make one we can actually solve. So I'm going to try and make a proportion that only has x's and numbers in it. So I don't want to match up x with y, even though those are corresponding sides. I don't want to involve two variables, but I can see that x here matches up with 25. So I'm going to go ahead and put the small stuff over the large stuff. Now I'm stuck in these two triangles. I don't want to involve z, don't want to involve y, but I got x here again, which matches up with 9. I got to put the small stuff on top. And look what just happened. I tried to make a proportion that only had x's in it, and it turns out I have a geometric mean proportion. Let's try and do it with y's. I see a y here, so y matches up with 25. And then I got 16 and y. There's another geometric mean proportion. Again, two of the diagonal pieces need to match to be a geometric mean proportion. The theorem says there's actually 3 of them hiding inside this one situation. Let's go find the last one. There's a z. I don't want to match up z with y. Let's match up z with 16. So I'm stuck in these two triangles, and then I'll do 9 and z. There's the 3 hidden geometric mean proportions inside this one situation. Now look where they came from. Here, the x, one of the geometric means came from this piece of the original situation. The other one came from the other side here. And the last one came from this middle section here, the altitude. You see, every other number came from the floor of this situation. A lot of times when I'm looking at this situation, I look at it like it's a tent. All right? So if we look at it as a tent and there are 3 poles holding up this tent, like if you're going camping, here's the floor of the tent. The 3 poles holding up the tent are the 3 geometric means. It doesn't matter whether there's an x there or a 4. You would put that number in twice. All right? So if In class, I'm going to show you a slightly simpler way so you don't have to do this every time. Breaking the triangles apart, copying these values over here, and then searching for proportions you can solve for. It's a lot of work. All right? And let's just try and remember. Here's how we solve. X times x, all right? That's x squared. 9 times 25 is 225. If I square root both sides, x is 15. Y times y squared. 16 times 25 is 400. Square root both sides, y is 20. Z squared equals 144. Square root both sides, z is 12. If we could make the proportions, we can solve them in a decent way. All right, so I hope you're watching this video. Remember, on the test, you'll have to be able to find the geometric mean of two numbers. Make sure you're using a proportion like this. And you're going to have at least 3 problems that looks like this. You're going to want to come to class and watch my trick on how to set these proportions up in a fast way. If you can set up a proportion, I truly believe everybody in the room can solve it. All right? Good luck, everybody.